Hi, how's it going? Welcome to Code with Z. In today's video, we gotta search through this 2D matrix that we have here. Why? Well, because that's what LeetCode 74 search a 2D matrix is asking us to do. As you can see, it says you're given an m by n integer matrix called matrix, with the following two properties. Each row is sorted in non-descending order. As you can see, each row is sorted in non-descending order, and the first integer of each row is greater than the last integer of the previous row. Well, as you can see, 10 is greater than 7 and 23 is greater than 20. So this is indirectly telling us that this is completely sorted. As you can see, this is completely sorted. And then let's see what we have to do with this matrix. It says, given an integer called target, return true if target is in matrix or false otherwise. And you must write a solution in log of m multiplied by n time complexity. So logarithmic time complexity. So if we didn't have this condition, it would be just really easy to just go through all of this matrix and look for numbers, right? But we do have this condition, and let's see how we can actually solve this. So for example, we're given this matrix here and our target is 3. So we basically have to look and see if 3 exists. And if it does, we gotta return true. And as you can see, it does exist. Now, since we can't loop through this matrix because that's going to give us the time complexity of n squared, we gotta do something else with the matrix. But this is not an ordinary matrix. We know that everything here is sorted. And I don't know about you, but when I hear about sorted numbers, searching for a number, and logarithmic time complexity, I immediately think of binary search. And you might be like, yeah, binary search would work if this was an array, not a matrix. Well, what if we turn it into an array? Or better yet, what if we treat it as an array? Now, what do I mean by this? Well, if we check, we have these rows that come after each other, right? What if we just kind of treat these as an array? Like so, we have 1, 3, 5, 7, 1, 3, 5, 7, 10, 11, 16, 20, 10, 11, 16, 20, and the rest, as you can see. As you can see, this one is this one here, and this 3 is this 3 here. You get the idea. And if these numbers were actually inside of an array, we would just have these indices, right? So this is the index of 0 that has the number 1 in it. And this is the position with the index of 1 that has the number 3 in it. And if we just kind of put these here, we're going to have something like this. So 0, 0. So this is the position with the index of 0. If this was an array, position of 1, position of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So currently what we're doing is that we're treating this matrix that we have here as an array to be able to apply binary search to it. So let's see if this actually works or not. So far, we have a pretty good theory. This is a sorted array, and binary search works on sorted array, and our matrix is sorted, so we have no problems with that. And we already have our indexes that we just defined ourselves. So let's see how we can apply binary search to this matrix that we have here. The first thing that we need to know is that how many columns we have. Well, let's count them. 1, 2, 3, 4. So we have 4 columns, 1, 2, 3, 4. Okay, so column number is gonna be 4. And how many rows do we have? Well, let's count them. 1, 2, 3. So we have 3 rows. So row number is gonna be 3. All right, we have these two defined. Now you're gonna see why we're gonna need this in a bit. But if we're applying binary search to an array, we're gonna need 3 important variables. The first one is going to be left, as we all know, and this is going to be equal to 0 because it's going to be equal to the index of the first position in our array, and that's going to be 0. And if this is equal to 0, that means left is pointing to this number that we have here because this is the number with the index of 0 if we treat this as an array, just like we saw in the previous slides. And then we also need another variable, and that's called right. And right is equal to the index of the last element inside of our array when we apply binary search. And to get that, we're going to say column number multiplied by row number minus 1. And that's going to give us the index of the last element inside of our matrix. So column number is 4 and row number is 3. 4 multiplied by 3, that's going to give us 12. 12 minus 1, that's going to give us 11. And would you look at that? 11 is the index of this number that we have here. So right is going to be pointing to this number that we have here. Now that we have our left and right, in binary search, we need our last variable, our last important variable, and that's going to be middle. So middle is going to be always equal to left plus right divided by 2. Left is 0, right is 11. 0 plus 11, that's going to give us 11. 11 divided by 2, that's going to give us 5.5. And we never keep the decimals, so we're just going to treat this as 5. So now middle is equal to 5, meaning middle is going to be pointing to the number with the index of 5, and that's going to be this 11 that we have here. Because if this was an array, This is the position with the index of 5. All right, then we're gonna be like, okay, let's get the value that middle is pointing to and check it and see if it is equal to our target or not. This is literally binary search. So we want to get this number that middle is pointing to, and if this was like a normal array, we would just say array at the index of m, and that would give us our 11. But because this is a matrix, if we want to get any of these values, we got to give it two variables, I and j. I is the number of the row that our number is at, and j is the number of the column that our number is at. So let's see how we can actually get I and j with these stuff that we have here. So far, we've only had binary search. The only part that's different is this, because the previous part, left being equal to 0 and right being equal to the index of the last element, and middle being equal to left plus right divided by 2, these are all textbook binary search. The only part that's different is that when we want to get the number that middle is pointing to, we can't just say matrix at the index of middle, because we have to give it two indexes. One should be pointing to the row number and one should be pointing to the column number. This is the only part that's different. Well, to calculate I, you can easily say I is equal to m divided by column number. Well, let's see. M is 5 because this is the position with the index of 5. So m is 5. 5 divided by column number is 4. So 5 divided by 4, that's going to give us 1.25. And we're not going to keep the decimals, so that's going to give us 1. And if we check, this number is indeed in the row with the index of 1. This is the first row and this is the second row. And as you can see, 11 is in the second row. And because our rows are 0 indexed, this row has the index of 1. And as you can see here, we're saying index of 1. Now, if we could only find the column number as well, we can easily get the number that middle is pointing to. Well, to calculate the column number, we can easily say middle mod column number. Let's check. 5 mod 4, 5 is middle and 4 is the number of the columns that we have. That's going to give us 1. And if we check, the index of this column that we have here is indeed 1. So matrix 1, 1 is going to give us 11 that we wanted to compare and see if it is equal to our target or not. So we're going to say if matrix at the index of I and j is equal to our target, well, we know I and j are 1, 1. So we're going to get the number that they're pointing to, 11. Is it equal to target? Target is 3. If it is equal to target, return true. Now really it's not, so we're going to be like, okay, because it's not equal to our target and 11 is greater than our target, we're going to say right should be equal to middle minus 1. Again, textbook binary search. The only part that's different is when we actually get the number that middle is pointing to. All of the other parts are literally binary search. So when we say right should be equal to middle minus 1, this is going to be 5 minus 1, and that's going to give us 4. So now right is pointing to this number, and we're going to look for our answer in this part of our matrix. So now that R is updated, we need to recalculate our middle. And again, middle is equal to left plus right divided by 2. And then we're just going to keep on doing this. Literally just a binary search until we find our answer. Now, let's code this in the simplest way possible. Alrighty, so the first thing that we need to do is to find the number of the columns that we have and the rows that we have inside of the matrix that we were given to. So we're gonna say const col number, this is equal to matrix at the index of 0, dot length, and then const row number, and this is equal to matrix dot length. Simple as that. And now we're gonna literally act as if we're doing binary search. We're gonna say let left be equal to 0 and let right be equal to, we saw how we calculate this in the slides. We said col number multiplied by row number minus 1, and this is gonna give us the index that right should be equal to. And then we're gonna say while left is smaller or equal to right, literally binary search, we wanna do the following. First, we're going to get our middle variable, and this is going to be equal to left plus right, and then divided by 2. But as you saw, we don't need the decimals, so we're going to say math.floor to get rid of the decimals that we might get. And after we have our middle, we need to find I and j to check the value that middle is pointing to. So we're going to say let I be equal to middle divided by column number, but we don't want decimals again, so we're going to wrap this around math.floor, and then we're going to define j as well, and this is going to be equal to, again, middle mod column number. And now that we have our I and j, we're going to check if matrix at the index of I and j is equal to our target, return true. If that's not the case, we're going to say else if matrix at the index of I and j is greater than our target, we want to say right should be equal to middle minus 1. Simple as that. and else, meaning if matrix at the index of I and j, meaning the number that middle is pointing to, is actually smaller than our target, we're gonna say left should be equal to middle plus 1. Literally textbook binary search. And if we didn't actually return true throughout our loop, we're gonna say return false at the end, because that means the number does not exist inside of our matrix. Now let's run it and see if we're gonna get accepted. I hope I've not made any typos, and awesome, we got accepted. Let me see if we can actually pass all of the test cases. And moment of truth, drum roll please. I'm just kidding. Awesome, we got accepted. Thanks for watching. Don't forget to like and subscribe, and keep on coding.